Ngalakin Khadijan Nyunga Boja.
Hello everyone, so welcome to the practical class of the ELEC 5505 in week 4. In last week, in the lectures, we have done the discussion of the short transmission line model, two-port network model, pi model, or in other words, pi circuit, plus medium transmission line model. And also in the practical class last week, I think we have already done the question number 1 and question number 2 of the 222, which are related to the short transmission line model and also the ABCD model, or in other words, the two-port network model. Okay, so I think the question number 1, question number 2 should be fine. And now let's move on to the next question, question number 3 of the 222. In this question, so we consider a medium-size transmission line. Okay, I think the keyword is medium lines. Okay, and represented by a nominal pi circuit shown in the figure below. In this given diagram, okay, we can see some similar things as we discussed in the short transmission line. First of all, at the sending end, we have the sending end voltage, sending end current. These are just voltage and current provided by the generators at the sending end. On the other side of the whole circuit, we can see we have the receiver side voltage, receiver side current. So these two things are the received factors at the user side. In between these two sides, we have our pi model or pi circuit of the transmission cable, which looks like, okay, the letter pi, something like that, okay? But regarding this particular question, because we are considering a medium-sized transmission line. So this model is slightly different from the short transmission line model. So please recall last week when we discussed the short transmission cable, we are saying, so during the transmission line, we just need to consider the line impedance, nothing else. In other words, we do not need to consider the admittance of the transmission line. That's true for the short transmission line model. But when we move on to the medium-sized transmission line, the story is changed. So in addition to the line impedance, so what is line impedance? So actually, in this diagram given in question number 3, you can see the capital Z equal to the lower Z by L. This capital Z is used to represent the total impedance of the whole transmission cable, transmission line. That's equal to the lower Z by L. The L is the transmission distance, the size of the line. The lower Z is the impedance of the transmission line per unit length. Okay, in other words, this part, the capital Z, remains same as what we discussed in short transmission cable. But what are the new items or factors in the medium length transmission lines? We mentioned, for medium length transmission lines, the total admittance cannot be ignorant anymore. In other words, we have to consider the total admittance. We are treating the total admittance of the medium length transmission line as the combination of two lumped capacitors. Okay, in this circuit, you can see we have two capacitors. One is on the left-hand side, in other words, the sending end. The other one is on the right-hand side, which is at the receiver side. So these two capacitors, I'm using blue highlighter here, these two capacitors are used to represent the total admittance of this medium-sized transmission line. Okay, so that. So this is just all the conditions we have. But regarding this question, what we need to do? We need to draw a phasor diagram. A phasor diagram for a lagging power factor condition at the load. Okay, another keyword is lagging power factor. So here we want to just remind everyone, what is lagging mean? Lagging means the current lags the voltage. But don't forget, when you draw the phasor diagram for such system, so the receiver side voltage, VR, is always used as a reference. Okay, now let's just start our analysis. VR will be used as the reference, no problem. But how about the other factors? like IR, RS, VS, VS here. So how to analyze the relationship of this IRS, VS with respect to VR? That's the key thing for this question. Okay, I think this analysis is pretty simple. First of all, based on this given circuit diagram, let's highlight two important nodes of circuit. First node is this one. Second node is given here. Now, for each of these two nodes, let's apply Kirchhoff current law. So, for example, for the big red node on the right-hand side, we define a current here. We say this to be current I. Current I going through the impedance of the transmission line and arrives at the receiver side. But after reaching this node, this one single incoming current I is split into two subcurrents. One is the IR going into the receiver, and the other current is going through the receiver side capacitor. So regarding this capacitor, so because it's at the receiver side, so we call that as a capacitor C at the receiver side R, so CR. The current going through this capacitor is called ICR. Again, CR denotes the capacitor at receiver side. Okay, this is what happened at receiver side. Now let's have a look at the node at the sending side. So for this right node on the left hand side, the sending side current IS is going into this node and then split into two subcurrents. One is the current I going through the impedance of the transmission line, and the other one is current going through the capacitor at the sending side. So I call that ICS, CS for the capacitor at the sending side. Okay, this is just what we have got. But if you have close look on the receiver side, again, receiver side means this side, you may find our VR, this voltage, in other words, the voltage across the two open terminals should be same as the voltage across this capacitor. In other words, we can write VR is equal to the voltage across the capacitor on the receiver side. Similarly, at the sending side, the VS, this voltage, is equal to the voltage across the capacitor at the sending end, like this one, equals VCS. Okay, this is just about the voltage. How about current? So we said we can use KCL to these two red color nodes in the circuit. So when we use the KCL, okay, this is the first part of the relationship. For the second part of the relationship, by taking the KCL at the left hand side, I mean the sending side, okay, node, we got IS, this incoming current, equals current I plus ICS, CS. And by using the KCL on the right hand side, or in other words, the receiving side, we got the current I equals IR plus ICR. Okay, so that. Now, let's think how to solve the whole question. First of all, as I mentioned at the beginning, so the VR, receiving side voltage, is always used as a reference. So here we can draw VR. But as what we have analyzed, VR and VCR should be equal. Okay, so VR is actually VCR. These two things are equal, same vector, same angle, same magnitude. Okay, everything same. Next thing, so we need to use the condition given the question. Question is saying, so please draw a phasor diagram for lagging power factor. What does lagging mean? So lagging means, as I mentioned, at the receiving side, the current at the receiving end, IR, is lagging the voltage at the receiving side. VR has been defined to be the reference. The IR must be slower than it. So lagging means slower, right? So the angle might be smaller than the angle of VR. VR got 0 angle, so IR must get a negative angle. But for this question, of course, we don't have any numerical values available, so we can just draw it generally, okay? So we assume VR is reference, IR is getting negative angle. That means this IR is lagging the VR. Sorry. Okay, IR is known. IR is given here. So maybe we want to determine what is the current going through the impedance of cable. In other words, we want to determine the I here. IR is known. This IR vector is okay. If we are able to know what is the ICR vector, so we should be able to determine the current I. What's ICR? ICR is current going through this right-hand side capacitor. How to determine ICR? Actually, if you focus on this capacitor only, so I just draw this capacitor by itself, okay? So this is the capacitor, we call that C, for example, at the receiver side. So CR thing. The current going through it is ICR. The voltage across it is VCR, right? VCR is same as our reference voltage, so it's the green vector in our plotting. And the ICR, VCR must have one important relationship. What's the relationship? The angle. What does it mean? Okay, you got one single capacitor, right? So the capacitor impedance is ZC, which equal to 0 resistance, because it's just a single capacitor. So 0 resistance plus J multiple 1 over J, sorry, my fault. Sorry, guys. It's 0 plus, normally it's just 1 over J omega C. Omega C, CR, whatever. We multiply J and J on both sides. So on top and bottom of the fraction is equal to 0 plus 1 over omega CR by J divided by J squared. But J squared is equal to -1. So this thing gives us JC equal to 0 minus J 1 over omega CR. This is how to calculate the impedance of a capacitor. But in the circuit, this DC impedance of the capacitor must follow Ohm's law. In other words, VCR should be equal to the JC, we call JCR anyway, JCR, okay, by ICR. So in other words, the JCR equal to VCR divided by ICR. This is just Ohm's law for capacitor, okay? So this JCR and this JCR are equal. So what we can say is VCR over the ICR equals negative J 1 over omega CR. So because for this question, we do not have any numerical values available. So this ratio magnitude is not so important for us now. The key thing is the negative J, because negative J is indicating the angle difference between the voltage and current across this capacitor. So in other words, this calculation, this result can be interpreted to be 1 over omega CR. So this is the magnitude of this phasor, followed by 1 negative J is corresponding to a negative 90 degrees angle. So in other words, such relationship is actually equal to or equivalent with VCR, voltage of the capacitor, equal to the current of the capacitor multiple some magnitude with negative 90 degrees. What's VCR? VCR is the voltage of the capacitor, but this voltage is a vector. This ICR is also a vector current going through capacitor. So in other words, VCR is VCR magnitude followed by the theta VCR equals magnitude of ICR followed by the theta, the angle of the ICR, by 1 over omega CR with negative degrees. Oops, we don't need this one. Now, if you focus on the angle only, this means this voltage angle for the capacitor is equal to this current angle of the capacitor with negative degrees. So regarding the angle, we can write down theta VCR is equal to the theta of ICR minus 90 degrees. That means for this capacitor at the receiving side, the voltage angle should be 90 degrees slower or lower than the angle of the current going through it. But in this question, for this particular question, the theta of the capacitor CR is the same as the angle of the VR. So this VR is the reference. So this angle is 0 degrees. That means the theta of ICR is equal to 90 degrees. Now we know the angle of current CR going through the right-hand side or the receiving side capacitor. So now we know this ICR must be 90 degrees. 90 degrees means it's pointing upward. But shortly, we want to use such relationship to calculate the I. So for now, I'm drawing the ICR vector at the end of the vector IR. So that means we will have, so I'm using black pen here. At the end of the IR, I'm going to draw an upward vector as ICR. So I'm drawing ICR here. This black one is ICR. Of course, again, we don't know the magnitude of it because we don't have any numerical values. We just assume it looks like this. Okay? Now, ICR is known. IR is known. The summation of these two vectors gave us the vector current I. Current I is current going through such line impedance. We have known the IR and the ICR. The summation of these two vectors should be the diagonal of these two vectors. So I'm doing here using red pen again. Okay. So this new vector, the red color one, is our vector I. Let me draw that. I'm drawing this one here. This is the vector I. Okay, so now we have half done this thing. Keep going. Okay, guys, sorry to say I have to just clean this circuit a little bit. Okay. Now we know for the middle part of the whole circuit, the current I is going through the impedance, and this current vector I is given in this phasor diagram like this. So when the current I is flowing through this impedance of the line, so the Z consists of R and X, so resistance and reactance. When the current I flowing through this resistance of the impedance of this medium-sized transmission line, resistor is not able to change the angle of the AC current or AC voltage. That means by use Ohm's law, the voltage of the resistor, so how can I just call that? We call that resistor. Yes, resistance. Okay. The voltage across resistance is equal to I multiple the R here. Okay. Sorry guys, just give me a second. Yeah. So the voltage across resistor is equal to the current I by the resistance. But we said for the resistance, its phase angle is 0. And so that means resistor is not able to change the angle between the current and the voltage across it. So such voltage across resistor must be pointing to the same direction as the current I. So here, at the end of the VR, we are going to draw a vector which is in parallel with the current vector. Okay, this dashed vector direction is in parallel with the current I. And its magnitude, for example, is here. This is actually I by R. This is indicating the voltage across the resistance of the transmission line. Okay, this first thing. Let's go back. So after going through resistor, so this current I will go through the impedance. And for this impedance is inductive. So it must be able to introduce a negative 90 degrees angle in the voltage across it. In other words, let me just slow down. Voltage across the inductance must equal to the current I multiple the reactance of this thing, because for such inductance, inductive reactance, it doesn't have real components, right? So it's just a J by X. So this is reactance. This J is indicating a 90 degrees phase angle change. So if the voltage angle of this thing is theta Vx, that must equal to the theta, the angle of the current I plus 90 degrees. That means the voltage angle regarding this reactance must be 90 degrees leading than the voltage of the must be 90 degrees leading than the angle of the current. Well, in other words, if you have already known the angle of the current, so the voltage across reactance must be 90 degrees leading. But here in this phasor diagram, we have already known the angle of the current is the angle of this vector, which is also the angle of this vector. Now, 90 degrees leading than this will give you, I'm using a green pen, this, okay, this angle is 90 degrees because of that J, okay? And the size of this new green color vector is, I think, I by XL. So this is I by XL, this magnitude of it, okay? So now, regarding the impedance Z of the transmission line, the total voltage across Z is actually IR plus IXL. In other words, this one, the dashed line is the voltage across impedance of this transmission line. Okay, but why do we need it? Because in our analysis, because in this part, our target is to determine the Vs vector here. Vs is equal to the voltage across the sending side capacitor. But if we apply a KVL to this loop, so let's just clean this part up, okay? So if you are using the KVL for this loop, the negative VCS plus the voltage across the impedance plus V receiving side capacitor is equal to 0. So this gives us VCS equals VZ plus VCR. But this VCS, as I mentioned, VCS equal to VS. You want to determine VS vector, you have to find the voltage across impedance and the voltage of the capacitor on the receiving side. This VCR, we have done that. The VCR is equal to VR. So that's okay. So now what I'm going to do is to determine the VZ. VZ can be interpreted to be VR resistors plus Vx. So we have done this part, right? So this dashed line is actually the VZ. This is our VZ. VR is the horizontal reference voltage. Vz is this vector given here. The summation of these two gave us the Vs, which is a vector starting from this point, go to the end. This is the Vs vector. Okay, so this is everything regarding this question. And I think, first of all, the vector calculation will be important. Secondly, lagging, leading information, you must be very clear. So which one is leading which one and which one is lagging which one? Okay, this second point. Still one, the circuit analysis will be important for such case. But I think that this part is not hard because it's just about KCL and KVL, these two rules. And the very last point is regarding some particular elements or parts. You need to understand their features. For example, if you got a capacitor, for capacitor, so as I mentioned earlier that the capacitor thing, yeah, here. For capacitor thing here, where is that? Let's highlight this one. Voltage for capacitor, the voltage across a capacitor will be 90 degrees lagging than the current angle. But for the inductor or inductive stuff, the current will be 90 degrees lagging than the voltage across the inductor. Okay, so such information will be important. Okay, this is the question number 2. I think we have explained the details of that, but my drawing is definitely terrible. I think this computer drawing result will be much better. Okay, so please refer to this part. Okay, this is the question number 2. Now let's move on to the question number 3. The question number 3, 60 hertz to 30 kilometers. Okay, keyword is 230 kilometers. 3-phase overhead transmission line. Because this distance is 230 kilometers, so this transmission line will be treated to be a long transmission cable. So in other words, this hint may be redundant because by reading the 230 kilometers, you should have already realized which model we should use. So long transmission model. Okay, and for this transmission line, the impedance is 0.8431 with 79.04 degrees ohm per kilometer impedance. So this is unit impedance. The shunt admittance is y equal to 5.1 by 10 power to negative 6 with 90 degrees Siemens per kilometers. This is unit admittance. The load at the receiving end is 125 megawatts at the unity power factor and at 215 kilovolts. Determine the voltage, current, real and reactive power at the sending end and the percentage voltage regulation of the line. Okay, these are all the questions. And because the question is asking us to determine the voltage current at the sending end, plus the power, the real power and reactive power at the sending end. So the real power and the reactive power at the sending end can be determined by using the sending end voltage and sending end current. So in this question, the key factors that we are going to determine will be the sending end voltage and sending end current. So in other words, the first thing we need to find out in this question will be Vs and Is. And after Vs, Is are determined, so we are going to determine the sending end real power. And what's the next one? Reactive power, Qs. Okay? But for such long transmission cable, how to determine the Vs and Is? So I think you should have known that. So ABCD model, of course, because we are using the 2 weeks time to determine to learn this ABC model. Okay, Vs as equal to, so just ABCD matrix multiple VR IR. ABCD, these 4 parameters are to be determined. The VR IR are just the receiving side voltage and the current. Okay, this is just the idea. But regarding this long transmission cable, how to determine the A, B, C, D, these 4 parameters. So here from our lecture slides, we have already known the A and the D. So the diagonal element of in this ABCD model matrix is equal to cos gamma L. And the B parameter is equal to the ZC sin gamma L. Finally, the C parameter is equal to 1 over the ZC sin gamma L again. Of course, in these 3 formulas, this gamma, ZC are to be determined first. What are these 2 things? Okay, let me just keep writing. So this is ZC is called characteristic impedance of the transmission line, and ZC is equal to square root the Z. This Z is the unit impedance divided by gamma. Unit is ohms. What's gamma? Gamma is called propagation constant. Propagation constant. Gamma equal to Z. So again, this lower Z is the unit impedance by the Y. Y is the unit admittance. Okay, so that. I just want to skip some calculation. Okay, so that should be very simple for you. By the way, regarding the cos and sin, these 2 functions, I think Professor Tyrone has already introduced the details in his lecture, but just in case you forgot it, okay? Oops. The sin gamma L is equal to, so half. The cos gamma L is also equal to half. On the top, so the factors used in these 2 formulas are equal. So they are all e power to positive gamma L, positive gamma L, and e power to negative gamma L, e power to negative gamma L. The same thing, but the signs are different. So for sin function, it should be just plus between these 2 differential functions. But for the cos function, it should be minus. Get that? Okay. And okay, after understanding this one, calculation should be easy. So let's go back to our ABCD model. Let me have a quick look on the condition of the question. Okay. So for solving this question, first of all, of course, we need to calculate the values of the A, B, C, and D, these 4 parameters by using the formulas given below. So in the solution, the detailed calculations are given here. So let me check here. See here, the cos function, the sin function are all given. So we have such result, such result. Sorry guys, I'd like to skip this calculation. So it should be very easy for you, and I don't want to take too much time on this. Okay, so the cos and sin functions are calculated like this. So the formulas used for these 2 calculations are given here. So please refer to this one plus the information given in the lecture to understand the calculation. Okay, so these 2 things are calculated. And for the ZC, let me check. Okay, the calculation are also given here. So you can see the ZC. So this is the characteristic impedance, which is equal to ZC. And for the gamma L, we used in the cos and sin functions is calculated here. Because the gamma equal to square root y by z, so you can see the square root y by z. L is the transmission lines is given here. Result is given like this. Okay, so this stuff are already. So that means in this long transmission line model, the A, B, C, D, these 4 parameters should be fine. You should be able to calculate them without any trouble. Okay, and the question is, what will be the VR and IR, or how to determine that? Let's go back to our condition. Okay. So now let's have a look at the voltage first. So in other words, I want to determine the VR first. So based on the condition given the question, we have known. So at the receiving end, see here, at the receiving end, the real power is 125 megawatts, real power, okay? At a unity power factor and at 215 kilovolts, this 215 kilovolts should be the line-to-line voltage at the receiving side. But we know from last week, so we want to convert such line-to-line voltage at the receiving side to the phase voltage. So we are dividing this 215 by square root of 3 for balanced system to convert the line-to-line voltage to the phase voltage. Result is given like this. So 124.13 kilovolts. But why the angle is 0 degrees? Same as what we discussed before. So we're always using the receiving end voltage to be the reference. So the angle is of course 0 for reference. Okay. So after this calculation, you got the VR vector at the receiving side is 124.13 with 0 degrees. So VR is confirmed, which is 124.03 with 0 degrees kilovolts. Okay, so this is the VR vector. How about the IR vector? So because you want to determine the current at the receiving side, and at receiving side, you know the voltage, you know real power. So the current IR is equal to, so I mean this of course vector is just the real power 125 megawatts divided by square root of 3 line-to-line voltage, which is 215 kilovolts. And the angle is theta IR. But how to determine this angle? So we need to use information about the unity power factor. Unity power factor means power factor at the receiving side is equal to 1. Unity is 1. But this angle is this number 1 power factor is equal to cosine theta. This theta is actually cosine theta V receiving side minus the theta I, theta I at receiving side. Cosine such angle equal to 1. That means the theta VR minus the theta IR will be equal to arc cosine 1, which is equal to 0 degrees. So that is indicating the angle of the voltage at the receiving side is equal to the angle of the current at the receiving side. The two angles are equal. But regarding the voltage, that is the reference. So the angle is 0. So for the current at the receiving side, its angle is also 0 degrees. So here you can see the current has a 0 degrees the angle, okay, at the receiving side. So 335.7. So this is 335.7 with 0 degrees. I think kilo amps, right? So amps. Guys, I didn't do calculation. I just leave that to you, okay? So amps. Now, regarding this ABCD model, we know on the right-hand side, ABCD is 4 parameters. We know VR, we know IR. So by doing this matrix calculation, you should be able to work out what is VS, what is IS. And I think that's really simple, right? So actually we have shown this calculation here and here. So how to calculate VS and IS. So done. The first part is done. So after you finish this calculation, this VS and IS should be the phase voltage and phase current at the sending end. Okay, based on this information, we need to determine what is the real power and reactive power. formula should be pretty simple. So regarding real power, of course, we are talking about the whole system, so including all three phases. So using square root of 3 multiple the magnitude of the, I think, phase voltage at standing end. So let me check where is it. So this is okay. I think we are using line to line voltage, right? Sorry for that. So here, square root of 3 multiple the magnitude of the line to line voltage, which is given here, and then multiple the line current magnitude, and this cosine theta. This theta is actually equal to the theta of the voltage at the standing end minus the angle of the current at the standing end. This voltage angle is given at here, so based on our calculation, and this current angle is given here. Okay, so just find difference of these two to be the theta, then cosine theta. You got such real power. For the reactive power, very similar, but just using sine function, nothing else. So this is how we calculate real power and reactive power at the standing end. Of course, you have another option. If you do not want to use the line to line voltage and the line current, you can use real power equal to 3 magnitude of the phase voltage at the standing end multiple the current of the phase. Actually, it doesn't matter because we assume that to be a Y connection, right? At standing end, then cosine. So theta Vs minus theta S, the same thing. For the rate power, same thing, but sine function. So result should be same as the result shown in the solutions. Okay, that's that. Finally, voltage regulation. So last week we have learned, so for calculating the voltage regulation, we use the no load voltage minus full load voltage divided by the full load voltage. The full load voltage, I think we have done our calculation somewhere, right? So here, we are talking about, of course, receiving side. So at receiving side, the full load voltage is actually the rated voltage, which is 124.03. So that number is given here. So full load voltage. And on the top, this thing is the no load voltage. But I think this is now new. Last week we have similar questions. No load means at receiving end, no load is used. If at receiving side you have no load, so the IR will be equal to 0. And the VR is actually the no load voltage. So in other words, we keep using the same ABCD model. So I just copy that here, okay? This time, VS IS staff equals ABCD model. And this time, we got V no load and 0 load current or receiving side current, which is nothing. And you want to solve the no load voltage. You have already known the standing end voltage. So we can say Vs equals A multiple the no load voltage plus B multiple 0. This term is gone. So no load voltage is equal to Vs over A. Okay, so here this no load voltage is used where that is used here. You can find if I zoom in a little bit. So this 137.86 is the standing side voltage magnitude. And this 0.89, where that 0.8904, this value is coming from our parameter A. So cos gamma L. cosh gamma L, which is parameter A. So this means, where is that? Where's my writing? Okay, here. So using the sending side voltage divided by the parameter A, you got no load voltage. Get that? Okay, so calculation is pretty simple. I think we have done that part. Okay, this is just all the questions regarding the tutorial 2. And we are going to move on to the tutorial 3. Okay, this is the tutorial 3 question sheet. And today we are going to cover question number 1 and question number 2 only. Okay, for question number 1, we got a single phase transformer has 2,000 turns on the primary side and 500 turns on the secondary side. So let's draw this thing up. Okay, so we got a transformer. So looks like this. And on the primary side, we have 2,000 turns, and on the secondary side, we have 500 turns. So we define turns ratio A to be N1 over N2. N1 means how many turns in the primary side coil. N2 means the number of turns in the secondary side coil. For this question, we got 2,000 over 500, which equal to 4. So this is the primary side. This is the second side. Okay, so this is what I have. Keep going. So the winding resistance for the primary side is R1 equal to 2 ohm. In the meantime, the leakage reactance at the primary side is 8 ohms. So in other words, this primary side coil is not ideal. It has the impedance. So how much is it? We call that as Z1, which is equal to R1 plus JX1, equal to 2 ohms resistance plus 8 ohms reactance. For the second side coil, the same thing. So we call that Z2. So as the secondary side coil impedance, which is not ideal as well. The resistance for the secondary side coil is 0.125 ohms, and the reactance is 0.5 ohms. 0.125 and 0.5. Okay, so ohms. This is just ohms. Okay, this is just information we have. But normally, we want to just translate such diagram into another style, which is easy for us to analyze. Okay, so we will just put that coil impedance separate from the ideal coil. So here we put, how to see that? On the primary side, we draw the things like this one. The 3 components inside of the dash box is used to represent the primary side non-ideal coil. And inside of this box, we have 3 elements. The first one is R1, the resistance, which is how much? 2 ohms. And the reactance, which is 8 ohms. Finally, we have one ideal coil. That means the reactance is, impedance are 0. Okay, because we have separated impedance from the coil. Okay, this is the primary side. And on the right hand side, regarding the secondary coil of transformer, we have similar thing, R2, X2, and the ideal secondary coil. So that means the impedance is 0 for this case, because we have put the R2, X2 separate from this coil. Okay, so if you want me to draw it again, so inside of the green box, we got this secondary side coil for this transformer. Okay, this is all the conditions we have. One more thing is the resistance load on the second side is 12 ohms. That means at the secondary side, we have one load. This load is a resistor. Its value is 12 ohms. So maybe you call that as R load, whatever. So part A is asking if the applied voltage at the terminals of the primary side of the coil of transformer is 1000 volts. In other words, we give 1000 volts between the two terminals of the primary side coil of the transformer. So please calculate V2 at the load terminals of the transformer. That means we want to determine what's the voltage V2. Okay. Now how to do this way? So actually, I'd like to move all the components of the second side to the primary side. So what we are going to draw is, I'm using blue highlighter. So R1, X1 will remain unchanged, and using yellow highlighter, R2, X2, and our load RL will be shifted from the second side to the primary side. Then we will produce such equivalent circuit. Okay. So R1, X1 doesn't change as mentioned. So all good. And we have 1000 volts input. But on the other side, we need to remove all two ideal coils and put all the components on the primary side to the primary side. So we will got, now I'm changing the color of pen to red, okay? Okay, so when we move the R2 from the second side to the primary side, its value will be changed. The new value will be R2 by A squared. What's A? A is turns ratio. Okay, so in this question, the turns ratio is 4, which is using the primary side coil number divided by the second side coil number. Okay, it's 4. And for the X2, same thing. So X2 will be changed to X2 A squared. For the load RL, same thing, RL by A squared. So in this equivalent circuit, we want to determine what's the voltage across this equivalent load. The voltage is denoted by V prime or V. We just go to V prime. I think this is okay, or maybe V2 prime, because 2 means the second side, right? V2 prime, but V2 prime is actually, it's actually equal to the turns ratio by V2. Of course, for this whole question, for part A of the question, the target is to determine the V2, but here we temporarily determine the V2 prime first. After determining the V2 prime, we calculate V2. This is the whole idea. I think solving this question should be pretty simple. So how to determine the question is asking us to determine the voltage, right? Yeah, how to determine the voltage V2 prime? You can use whatever you learned before, KVL, voltage division, or whatever method you want to use to solve V2 prime. I think in the solution, we used the Ohm's law. First of all, we determine what is current, I1. I1 equal to this total voltage supply, so 1000 with 0 degrees, because we are using this one as reference, so angle is 0, divided by the total impedance in the equivalent circuit, which is given here. So R1 is how much? Let me check. R1 is 2 ohms, and X1 is 8 ohms, but this should be 8J ohms, okay? And R2 is 0.125, 125. Multiple A squared, A is 4, so 4 squared. And keeping this one is the X2 is 0.5, so 0.5 multiple 4 squared. Don't forget J. And finally, RL A squared should be 12 by 4 squared. But this is just resistance. So you need to just calculate the total impedance of all these seriously connected components. So 2 and this thing and this thing are the resistance. So 2 plus 0.125 by 4 square plus 12 by 4 square. This total resistance REQ plus J by the how much? 8. So 8 plus 0.5 4 square. This is the x equivalent reactance. The sum of them give you total ZeQ. I think the value should be pretty easy, right? Quickly. This is 16. Multiple this one give you 2. 2 plus 2 is 4. 4 plus 12 by 4 square. 192. So that means 192 plus 4 plus J multiple 8 plus 16 divided by 2 is 8. So that's give you 196 plus J 16 ohms. Okay, this number is the total impedance of all the elements in this equivalent circuit. And then the current is equal to, I think they call this as I1. So I1 is given here. So I1 equal to 1000 with 0 degrees total voltage supply divided by this 196 plus J 16 ohms total impedance. The result I just copy from solution is 5.08 with negative 4.67 degrees amps. And this I1 is the series current for all the elements. So regarding the V2 prime, V2 prime is equal to I1 multiple this equivalent load impedance, which is RL by A square, equal to this number is the I1 multiple RL, the load is 12 ohms by 4 square. The result is how much? Is 975.4. I'm just copying the answers. Okay, volts. But we said this V2 prime is actually equal to A by V2. Our target is to determine the V2. So V2 is equal to V2 prime over 4. So you can just finish calculation by yourself. Okay, that's that. So this is regarding how to determine the load side voltage from the transformer. Regarding this part, I think using this Ohm's law is okay, not very complicated, but I think maybe using voltage division may be much faster. But anyway, I leave that to you. You can try it out by yourself. I think calculation is easier if you want to use voltage division. The result must be exact same. Okay. Okay, this is about part A of the question number 1. Keep going. Part B. If the voltage regulation is defined as the difference between the voltage magnitude at the load terminals of the transformer at full load and at no load in percentage of full load voltage, with input voltage hold constant, compute the percent of voltage regulation. Actually, this part B is using 3 lines to tell us what is the voltage regulation, but we have already learned it before, so we can just keep using that. Okay. Voltage regulation is equal to no load voltage minus the full load voltage divided by the full load voltage by 100%. And these 3 terms, sorry, my fault. The 2 terms, no load voltage and full load voltage, are all just magnitudes. The others are all numerical values. Okay, this gives us, so let's have a look. I think the full load voltage, this term and this term, has already been determined in our part A calculation. So I didn't copy down the final answer, but we can write this down. Okay, so easily. So the V2 should be equal to, from part A, 243.8. Again, I'm copying the answers. Okay, 7 degrees volts. But this V2 is the voltage across that 12 ohms load resistance. So in other words, this is the full load voltage. Regarding the voltage regulation calculation, we want to use the magnitude of the full load voltage. So in other words, we just need to copy this 243.8, this number, into the formula. So here we go back to here. Yeah. That's equal to for this full load voltage, we just copy number is 243.8, 243.8, 100%. This stuff. The only thing left is the no load voltage. No load voltage means there's no load is connected to a circuit. But in this question, we are facing a transformer circuit. If you want to calculate what is the no load voltage for this transformer implementation, we need to remove the load from the circuit and then keep the terminals open. Under this situation, what is voltage V2? That will be the no load voltage. But because the two terminals becomes open and no current can go through these two terminals, so current is equal to 0. If the current is equal to 0, when the current goes through this R2, X2, so 0 by this impedance, the voltage drop is equal to 0 as well. Then this V2, no load voltage, is equal to the voltage across the two output, equal to the voltage difference across the two output terminal of the secondary part of transformer. How to determine this V? We call them what? We call them as V prime, for example, okay? So that means V no load is equal to V prime. V prime is the output voltage from the secondary side of transformer. That's equal to V1 divided by the A. A is the turns ratio, okay? But V1, which has been known, is 1000 volts with 0 degrees. Divided by A is 4, is 250 with 0 degrees volts. Here, for the no load voltage, we just need to use the magnitude of it, so which is 250, okay? So 250 is given here. And then by finishing this calculation, you got the voltage regulation, which is equal to 2.54%. Then finish. Okay, this is the question number 1 of tutorial 3. Let's move on to the very last question for this session. Question number 2 of tutorial 3. A single-phase step-down transformer is rated 15 MVA, 66 kilovolts, 11.5 kilovolts. So this is just to read the voltage ratio between the primary side and secondary side of transformer. With the 11.5 kilovolts winding short-circuited, rated current flows when the voltage applied to the primary side is 5.5 kilovolts. The power input is rated as 100 kilowatts. Please determine the equivalent resistance and reactance on the primary side in ohms, referred to the high voltage winding. For this question, I think the keyword is about the short circuited. Yep, get that. So let's start from scratch on this question. First of all, we got one transformer. So just draw this stuff out. So primary side and second side. And on each of these two sides, we have the resistance and the reactance. So we call them R1, X1. And on the second side, we have the same thing, R2 and X2. Okay, this whole thing here. Okay, this transformer. And for this question, because at the secondary side, it's got short circuited. So first of all, why did you say this is the secondary side? Because the question is saying, so with the 11.5 kilovolts winding, this 11.5 kilovolts winding means this 11.5 kilovolts here, but this side is on the primary side. Normally, this is the primary side, this is the second side. But because this number is same as this number, so I understand this is talking about regarding the second side, we got a short circuited or short connection or short circuit, the same thing. So in other words, we are using a short wire to make a short connection between two terminals at the second side of the transformer. Same as what I've done in the question number 1. We are going to reflect the second set to the primer set. So what we are going to do is all the components on the primer set will remain unchanged. So R1, X1 is not moving. But this R2, X2 will be shifted to the primer set by multiplying them with A square. So R2 becomes R2 A square. X2 is changed to X2, X2 A square. And then for this single short connection wire, it's still a wire, nothing has changed. And then go back. And in this situation, so what's next condition? Let's have a look. Rated current flows. In other words, after we make such short connection, so in this equivalent circuit, the rated current is flowing through. So this rated current can be determined by using the rated power and rated voltage. So we temporarily call that as I1. So we are going to calculate I1 very soon, okay? And when the voltage applied to the primary set is 5.5 kilovolts. So regarding these two terminals, we are giving a 5.5 kilovolts input voltage. Okay, this is all the conditions we have. In this situation, the power input is 100 kilowatts. Real power, of course. Okay, P equals this one. The question is asking us to determine the REQ1 and SEQ1. So the equivalent primary set resistance and reactance. Okay, how to do that? So first of all, let's just calculate I1. So regarding I1, because we know the I1 is a rated current, the rated current is equal to, so we can use the rated power divided by rated voltage to do that. So we are using 15 megavA divided by how much? 66 kilovolts. So here you may have some questions. First of all, why don't you consider the angles? Yes, we should. But regarding this rated current, we want to know how strong the current is. The phase angle difference is not included in the rated terms. So we do not need to consider angle temporarily. Okay. But regarding this I1, we should consider angle. Okay. Secondly, why did you divide it by 66 kilovolts? Why don't you divide that by 11.5? The reason is we have already put all the components to the primer set. And at primer set, we are giving or we are providing the rated current, rated voltage, rated power to make the whole circuit working. So all our discussions are within the primer set. So of course, we should use the primer set rated voltage. This primer set rated voltage is given here. Okay, so rated voltage. So based on this calculation, based on this formula, we can go to the answer is 227.3. Okay, just copy this one here. This one is the rated current, I1. Okay, now I1 is known. And we know for this rated current to flow through the circuit, the voltage applied to this primer set terminals is 5.5 kilovolts. And the real power is 100 kilowatts. So let's have a look how to determine the equivalent resistance and equivalent reactance. Please recall 2 weeks or 3 weeks ago when we introduced the derivation of the AC circuit, we mentioned only the resistor can consume real power. In this question, the real power is given to be 100 kilowatts. This 100,000 watts, did I say the right thing? Yeah, the real power is 100,000 watts. This 100,000 watts real power must be consumed by all the resistance in the circuit. In other words, R1 and R2 A squared, summation of the two consume all the real power. Okay, so we say the equivalent resistance is equal to R1 plus R2 A squared. the real power consumed by these two things is equal to, real power is equal to I1 squared by IQ. This I1 is kind of flowing through them because all the components are kind of in series. So I think this formula is just like that. I1 is shared by these two resistance stuff. Okay? So in this question, I1 is known, P is known. So you can evaluate IQ equal to P over I1 squared. So again, I don't want to copy down the whole work given here. Result is 100 by 10 power to 3 divided by 227.3 squared. The result is how much? 1.94 ohms. So this is the first step. Regarding the second step, we want to determine what is equivalent reactance equal to this. Equal what? We know before the total equivalent impedance, the ZEQ equals REQ plus J multiplied by XEQ. The magnitude of this equivalent impedance should be equal to square root REQ squared plus XEQ squared. So that means real part square plus the imaginary part square, then square root the sum. Get that? Now, our question is to determine what is the XEQ. Now, what you can do is we square both sides. Which gives ZEQ magnitude square equals REQ square plus XEQ square. So the equivalent reactance is equal to square root the magnitude of impedance square minus the equivalent resistance square. REQ has been solved here, so that is no problem. The only question is what is equivalent impedance ZEQ? This is ZEQ. It can be determined by using the voltage and current. Okay, because in this whole question, the ZEQ is actually total impedance, which actually should be equal to R1 plus R2A square plus J multiple X1 plus X2A square stuff. Right? And we know the total given voltage is 5.5 kilovolts. So V equal to I1 by ZEQ is equal to 5.5 kilovolts. I1 has already been determined. Where's I1? I1 is here, 227.3 amps. So we can keep writing here the ZEQ equal to V over I1. Ohm's law is 5.5K divided by 227.3 amps. So result is 24.2 ohms. So this is actually the total equivalent impedance. Of course, the angle should be included, but in this question, first of all, we don't have any angle information. Secondly, we just need to know the magnitude of the ZEQ. So this calculation is actually calculating magnitude of ZEQ, which is 24.2 ohms. Now this is known, so 24.2 square minus REQ square. REQ equal to how much? I remember. 1.94 ohms, right? Yeah. REQ equal to 1.94 ohms. So minus 1.94 ohms square, then square root. You got the equivalent. Oh, sorry. I think I wrote wrong thing here. Okay. Sorry for that. So I mean the magnitude of the ZEQ is equal to 24.2 ohms. After knowing this one, the equivalent impedance is equal to square root 24.2 ohms square minus 1.94. Okay, 1.94 ohms equivalent resistance square. Result is equal to 24.12 ohms. So this is the equivalent reactance. Then I finish. Okay, everyone, thank you very much.